You're looking at an address that doesn't exist. The Virgo Supercluster, that cosmic neighborhood astronomers have pointed to for decades as our place in the universe, turns out to be a provisional label for something we fundamentally misunderstood. We drew borders around the wrong territory. We named a structure that was never actually a structure. And realizing this required rethinking what it means for anything in space to be grouped together at all. Here's what makes this so disorienting. For most of the 20th century, astronomers operated under a reasonable assumption. Galaxies cluster together. Clusters group into superclusters. Superclusters represent the largest gravitationally bound structures in the cosmos. Simple hierarchy. The Milky Way belonged to the local group, which belonged to the Virgo Supercluster, which contained roughly 100 galaxy clusters spread across 110 million light-years. Clean taxonomy. Except none of that hierarchy actually reflects how the universe organizes itself. The problem revealed itself slowly through something called peculiar velocity. Galaxies don't just ride the expansion of space like leaves on a river. They also move through space, pulled by gravity toward concentrations of mass. These local motions, peculiar velocities, trace invisible architecture. Where galaxies flow reveals where mass actually concentrates, regardless of what optical telescopes show. And when astronomers finally mapped these flows in detail, the picture that emerged looked nothing like the neat Russian doll structure everyone expected. Imagine you're standing in what you think is a small town. You can see the buildings around you, the streets, the obvious boundaries. Then someone hands you a map showing traffic patterns, and you realize the town is actually the corner of a metropolis 50 times larger. The boundaries you perceived were arbitrary. The traffic flows to a downtown you didn't know existed. That's what happened when we finally saw the universe's peculiar velocity field clearly. A 2014 study led by Brent Tully used data from thousands of galaxies to trace these motions backward, mapping which galaxies flow toward which gravitational basins. The Virgo Supercluster, that supposed gravitationally bound structure containing our local group, dissolved under scrutiny. It wasn't a real basin at all. The galaxies we'd grouped into Virgo were actually draining towards something incomparably larger, a gravitational attractor so massive it redirects the motion of everything across 500 million light-years of space. They named it Laniakea, Hawaiian for immeasurable heaven. The name fits in ways that go beyond poetry. Laniakea contains roughly 100,000 galaxies with a total mass around 100 million billion times the Sun. The old Virgo Supercluster, the thing we thought was our cosmic address, represents maybe 4% of Laniakea's volume, a single appendage, one branch on a structure so vast that light takes 520 million years to cross it. But even calling Laniakea a supercluster creates confusion, because it's not defined the way Virgo was. Virgo was defined by galaxy density, by drawing borders around regions where galaxies appeared concentrated. Look through a telescope, count galaxies, draw a boundary. Visual taxonomy. Laniakea is defined by dynamics, by mapping which galaxies share a common flow toward a central gravitational basin. It's the difference between grouping people by where they stand versus grouping them by where they're all walking. One method relies on a snapshot. The other reveals underlying structure. The Great Attractor sits near Laniakea's center, a gravitational anomaly that's been puzzling astronomers since the 1970s. From our position in the Milky Way, we're rushing toward it at roughly 600 kilometers per second, dragged by gravity across hundreds of millions of light-years. But the Great Attractor isn't visible directly because it lies behind the zone of avoidance, a region where the Milky Way's disk blocks our view of distant space. We can detect its gravitational influence without seeing the mass causing it, like feeling a magnet pull through a sheet of paper. For decades, this created a navigation problem. We knew something massive was pulling us, but couldn't map the full structure because our own galaxy blocked the view. Only by measuring the peculiar velocities of thousands of galaxies in all directions could astronomers reconstruct the basin's true extent. Laniakea's boundaries mark where that inward flow stops, where galaxies begin falling toward neighboring basins instead. Those boundaries aren't sharp lines. They're watershed separates, like continental divides, where rainfall on one side flows to the Atlantic and rain on the other side flows to the Pacific. Step across the divide and you're in a different basin, even though the landscape looks identical. Laniakea's borders work the same way. Cross them, and galaxies fall toward the Shapley Supercluster or the Perseus-Pisces Supercluster instead. Different gravitational watersheds. But here's what makes this deeply strange. Laniakea, despite its scale, isn't actually gravitationally bound. The universe's expansion is pulling it apart faster than gravity can hold it together. In conventional terms, that means it's not a real structure at all. Gravitationally bound was supposed to be the definition of real in cosmic architecture. If something can't hold itself together against expansion, calling it a structure seems questionable. Yet Laniakea is more real than Virgo ever was. It represents an actual dynamical system, a region where galaxies genuinely share a common motion and a common fate, at least temporarily. The fact that expansion will eventually tear it apart doesn't erase the structure that exists now. It just means cosmic architecture operates on rules we're still learning to read. This is where the true scale problem emerges, not just in Laniakea's size, but in what its existence reveals about structures beyond it. Part 1. Word count. 1,000. Laniakea flows into something larger. Map enough supercluster basins, trace enough peculiar velocities across enough cosmic volume, and a structure emerges that makes Laniakea look provincial. The Pisces-Cetus supercluster complex stretches across 1 billion light-years, encompassing dozens of superclusters, including Laniakea itself. Not a gravitationally bound object, obviously. Nothing at this scale can resist expansion's pull, but a genuine structure nonetheless, visible in how matter organized itself during the universe's first few 100 million years. These complexes don't exist in isolation. They connect through filaments, sheets, and walls that span observable space. The Sloan Great Wall extends 1.4 billion light-years, discovered in 2003 when astronomers mapped galaxy distributions from the Sloan Digital Sky Survey. It's not a solid object. It's a concentration of galaxies and dark matter, forming a coherent thread through space, held together not by current gravitational binding, but by the initial density fluctuations that emerged from cosmic inflation. This is where conventional vocabulary collapses completely. Calling these things structures implies permanence they don't possess. Calling them temporary ignores that they've existed for billions of years and will persist for billions more before expansion erases them. They're real, but not bound. They're organized, but not stable. They exist in a category we don't have proper language for, patterns frozen by expansion into configurations that will eventually dissolve. The cosmic web itself represents the largest organizational pattern in the universe. Billions of years ago, tiny quantum fluctuations in the infant universe's density field got stretched by cosmic inflation into macroscopic variations. Regions slightly denser than average had slightly stronger gravity. They pulled matter inward, growing denser still. Regions slightly less dense lost matter to their neighbors, becoming voids. This feedback process, playing out across cosmic time, produced the web we observe today. Simulations running on supercomputers can reproduce this structure with disturbing accuracy. Start with initial conditions matching the early universe's density fluctuations. Add dark matter, regular matter, dark energy, and the laws of gravity. Run the simulation forward 13.8 billion years. The result matches real observations of galaxy distributions so closely that you can't reliably distinguish simulated universes from ours without checking the metadata. These simulations reveal something profound about scale. The cosmic web's structure emerges inevitably from the universe's initial conditions and fundamental laws. It's not random, it's not arbitrary. Given the physics we observe and the density fluctuations we measure in the cosmic microwave background, this specific web pattern was essentially predetermined. Different initial fluctuations would produce different detailed arrangements, but the overall character, filaments, walls, nodes, voids, would remain the same. The architecture is baked into how gravity and expansion interact. But here's what the simulations also show. The cosmic web represents the largest scale at which structure exists at all. Beyond roughly 1 billion light-years, the universe becomes statistically homogeneous. Pick any cube of space that large, and it contains approximately the same density of matter, the same distribution of galaxy types, the same ratio of voids to filaments. Increase the cube size, and the homogeneity improves. The universe has structure at small scales: stars, galaxies, groups, clusters, superclusters, but approaches perfect smoothness at the largest scales. This is the cosmological principle made manifest. The universe has no center, no edge, no special locations. Of a supercluster complex threaded through a supercluster that's part of a supercluster complex threaded through the cosmic web, and so does every other observer anywhere in the universe. We're not special. We're not central. We're not in a privileged position. We're just here, in a structure that's representative of structures everywhere. The observable universe contains all of this web structure out to a distance of 46.5 billion light-years in every direction. That's not the universe's actual size. It's just how far light has had time to travel since the Big Bang, accounting for expansion. The actual universe extends far beyond what we can see, possibly infinitely far. Every point we observe was once near us in the dense early universe before expansion carried it away. We're seeing ancient light from regions that are now vastly more distant than they were when that light left them. This creates a disturbing realization about cosmic architecture. Everything we've discussed, galaxies, groups, clusters, superclusters, the web itself, exists only in our past light cone. We're observing how these structures looked millions or billions of years ago when their light began its journey to us. The Virgo cluster we see is Virgo as it existed 65 million years ago. Laniakea's center is 250 million years out of date. The Sloan Great Wall shows us structure from when Earth's continents were just beginning to separate. We're not observing the universe as it is. We're observing its history, arranged by distance into a timeline we experience as space. The universe we inhabit extends beyond what we can see, beyond what light has had time to reach us from, into regions we'll never observe, no matter how long we wait, because expansion is carrying them away faster than light can close the distance. The cosmic web we've mapped represents only the visible portion of a structure that extends indefinitely beyond our horizon. There's no reason to think it ends. There's no reason to think structure fundamentally changes beyond what we can see. But we'll never know for certain, because those regions are permanently beyond observation. We're inside the architecture, trying to understand its full scope from a single vantage point that can see only so far. Every measurement we make, every structure we identify, every scale we comprehend, exists within that fundamental limitation. We're mapping infinity from inside a sphere. The Virgo Supercluster doesn't exist as we thought it did. That's not a failure of astronomy. It's what understanding looks like. We named something based on what we could see, then discovered we were looking at the wrong structure entirely. The actual architecture operates at scales and through dynamics we couldn't perceive until we developed tools to measure how galaxies actually move, not just where they appear to sit. Laniakea is our address now, though it's no more permanent than Virgo was. Expansion will eventually erase it. The cosmic web itself will gradually dissolve as dark energy pulls space apart faster than gravity can hold anything together. Give it enough billions of years, and every structure we've discussed will disperse into isolated points of light, then darkness. But right now, in this epoch, the web exists. The flow patterns are real, and we're finally learning to read them correctly.